Coulombs Law. Your priming questions are, what is the relationship between all of the variables? And then, since it is a force, what must you take into consideration? All right, so Coulombs Law. The magnitude of the electrostatic force between 2-point electric charges is directly proportional to the product of the magnitudes of each charge and inversely proportional to the square of the distance between the charges. All right, so that sounds complicated until you look at the equation. So what we have here is this equation. The electrostatic force is equal to K. This is the constant, 9 times 10 to the 9th Newton meter squared per Coulomb squared. So K times Q1, Q2 divided by D squared. Now, this equation you may or may not be familiar with. This is actually the truest equation that we have for gravity. So the force of gravity, also known as weight in some cases that we've talked about, G m1 m2 over r squared. So you can tell from these equations that these equations are very similar. And we can actually use both equations to describe the force between two particles if they are charged and have a mass, which we'll show you in just a little bit. And this constant, 9 times 10 to the 9th, requires you to be in newtons, meters, and coulombs for all of these. So you do need to be very careful of your units. If you're in kilometers or in millimeters or in microcoulombs, you need to convert all of those to our standard base units that you see here, newtons, meters, and coulombs. Otherwise, you won't be able to use this particular constant. So you do have to be careful of your units. So if we look at this, this is just showing you how we get our units for our K. And our K value, as I showed you before, are newtons meter squared per coulomb squared. And if you look at this, this is why. We need to have our force in newtons. And we have K times coulombs, or Q1, Q2 over D squared. So it's coulombs times coulombs over meters squared. So this is what it would look like. Over here. And so we use our K so that our units can cancel out so that we can get our newtons over here. If you have questions about this, we can talk more about this in class. And so, what I want to show you is the force between two particles, a proton and an electron, the force of the electrostatic force compared to the gravitational force. And so, I have the equations here up at the top. All you need to do for this is plug into both and get the force for both. So this one is going to be the electrostatic force. This one's going to be the gravitational force. You can pause the video. I'm just going to write the answer and do a quick discussion on it. So the answer to this one is 8.2 times 10 to the negative 8th newtons. Which if you did this one first, this seems like a really small value. And it is until you do the next one, the gravitational force. So we have 3.7 times 10 to the negative 48th newton. And this force is amazingly smaller than this one. And so here, the difference here is roughly 10 to the 40th between these two forces. That's a huge difference. And this brings us to a quick conversation about the forces that we know of in this universe. We have three main forces that we're going to work with. Some can still consider them to be four. The first one is going to be the strong nuclear. And this is essentially what holds our atoms together. The second most powerful is going to be the electroweak. And this is what we are spending our entire second term really talking about. And the third, or the weakest force, is going to be our gravitational force. And this is what we spent term 1 on, and this will be term 2. This, the strong nuclear force, this is what you were really talking about in chemistry. So term 1 and term 2. All right, so this gives you an idea of how different the power between 2 and 3 is. It's 10 to the 40th when we're looking at the scale of a proton to an electron. All right, let's keep moving. The next equation that you want to be familiar with is if you are looking for the number of electrons, and I should say the number of excess electrons on a charged object, and this could be excess or lack of electrons on a charged object. So the number of electrons is going to be equal to the capital Q, which is the charge of the object, divided by the little lowercase q, and this is the charge of an electron, 1.6 times 10 to the negative 19th coulomb. And so as a quick check, we can work on this first one. How many electrons were removed to produce a 7.2 millicoulomb charge on a metal sphere? We can work it out, and this is what you should get. And we're going to show you this one. We can work on this one in class if you have any questions. How many electrons were added to produce a negative 8.6 microcoulomb charge on a metal sphere? Work that one out, and we'll discuss in class. Now, what I want to show you is this problem. In this case, we have 3 particles in a line. And with these 3 particles, the charges are given. These are mu's, so these are microcoulombs that are given. We're told that Q1 is negative, Q2 is positive, and Q3 is negative. And what we are asked to find is the net force on particle 1 due to the other 2 charges. And so when we look at this, we think back to our electrostatic force equation, Fe is equal to KQ1 Q2 over d squared. And what we need to find is the net force acting on our Q1. And so when we do this, we will do the electrostatic force between Q1 and Q2 first, find the force, and then we'll do the force between Q1 and Q3 separately. What we do with this is when we are working with a multi-particle system, we only work with 2 at a time, and we completely ignore the other charges. We will take them into account separately, and then we will add those forces up together at the end to find our net force. And so let's go and start working this out. So if we want to find the force between 1 and 2, so that's 1 and 2, we write out our K. So 9 times 10 to the negative 9. Oh, sorry, 9 times 10 to the 9th times our Q1, which is going to be negative 3 times 10 to the negative 6 times our Q2, which is 5 times 10 to the negative 6. This divided by the distance between Q1 and Q2, which is going to be 0.3 squared. And when we work this out, let me go and do this. 9e9 times 3 negative 6 times 5 negative 6 divided by 0.3 squared. I get 1.5 newtons. Now, if you think back to this, if you look at this, this will come out as a negative. This negative is really there to give you some information. If you go back to our definition from up here, we really are only working with the magnitudes in the equation. What we need to do with this is we need to look at these charges and figure out whether it's going to be an attractive force or a repelling force. And the way to do that is to look at the charges and see if they're opposite charges, they're going to attract. If they are equal charges or the same type of charge, both positive or both negative, they are going to repel each other. In this case, between Q1 and Q2, they are opposite charges, so Q1 will be attracted to Q2, so this force will be going to the right. So rather than saying negative 1.5 here, what I would recommend actually would be to not worry about the negative and simply say it's 1.5 newtons to the right. Now when we work out force 1 to 3, we start this out the same way. So we have 9 times 10 to the 9th times 3 times to the negative 6, again The negative doesn't matter, but you can put it in if you want, times Q3, which is negative 4 microcoulombs, so negative 4 times 10 to the negative 6, divided by the total distance, which is going to be 0.5 squared. And this gives us this is going to be equal to 0.432 newtons. Now, when we look at this, between Q1 and Q3, they are both negatively charged, so this one is going to be going to the left. So this one is going to be 0.432 newtons to the left. And now, what we want to do is we can create a quick free body diagram, if you're familiar with those. You don't have to in this particular case. And we have one force going to the right, and we have one force going to the left. So we have one force going to the right, and we have one force going to the left. And let's go ahead and label these forces. The one to the left is going to be 0.432 newtons. The one to the right is going to be 1.5 newtons. And so the net force, the sum of the forces, is going to be, and we'll go and set right as positive, so it's going to be 1.5 minus 0.432. So 1.5 minus 0.432 gives us, and let's see how many sig figs do we have. We actually only have one significant digit. The calculator will give you 1.068 newtons, and this will be to the right. If we were to put this in the correct sig figs for this would just be 1 newton to the right. And there you go. All right, the problem that I want to leave you off on is this. It's a similar problem, just a little bit different. Find the net force on particle 2. Attempt this. We'll go through this more in depth in class.